Well, good day and welcome to part 2 of our matrix multiplication lessons for general mathematics. And I'm going to talk about the second part of this, which should actually be a bit shorter. I know the last lesson was quite long. This will be a bit shorter, just a couple little extra tidbits that you'll need to know and be aware of, a little bit more language, and then you should be right to finish the exercise. And realistically, this is very procedural, but it's probably the hardest thing you'll do in this topic. So let's start with identities. Now, you've been dealing with identities your whole mathematical career. You just probably don't really realise it. So a mathematical identity does nothing. And that's kind of the point of an identity. And it's really important for high-level mathematics to know. It's kind of like getting back to home base if you're playing baseball. You've achieved nothing, you're back where you started. But the identity is a definition of that. So let's consider it in the sense that you need. What does nothing in the following cases? So in the first one, what plus 7 equals 7? We know that the additive identity, so the identity for addition, is 0. 0 does nothing when we add or subtract it. And for multiplication, we know that this is 1. The number 1 times 7 does nothing. It changes 7 not at all. And it's the same for division. So we've got 0 and 1 are identities that you've been dealing with for a long time already. So what about matrix multiplication? What's the identity for matrix multiplication? Now it turns out that the identity is 1, 0, 0, 1. This is a 2 by 2 identity, by the way. And this will work for multiplying anything where we need to match our number of columns to our number of rows. So if we're multiplying a matrix that has 2 rows, then we'll need to use the 1, 0, 0, 1. But if this has 3 rows, we need to use a different identity. So there's different identities for different matrices, and we'll talk about that in a second. So the identity is always a square matrix. Why is that the case? The identity always looks like this, 1, 0, 0, 1. Why is that the case? I'm going to encourage you now to take a minute just to have a think about why these things might be true. Okay, so hopefully you had a good consideration about that. You've really thought through the process. Now let's have a look at what I've got under here, which I can't actually remember what I've got under here. So let's see. Here we go. So these are the identities, but in ascending order. So the identity always has that leading diagonal, top left to bottom right of 1s. And so it means the next identity will be 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. Now identity always has to be square because you want to get your resultant matrix to be the same dimensions as the original matrix. So you'll end up with a square matrix, and that means you can multiply by the identity on either side. The dimensions always match. So it'll always be square to follow that pattern. And the identity will just keep on getting bigger like that. But let's be honest, if you're dealing with the identity, which won't be much in general maths, it'll come up as a 2 by 2, maybe a 3 by 3. And that's it. Okay, let's talk about matrix powers. We can calculate A times B, but what about A squared? Well, hopefully you recognise that A squared is just equal to A times A. That's all it is. So that's our A squared value, and you can calculate that if you need. Let's do a worked example. Calculate A squared where you can. So I might just need to create a bit more space. Maybe even a bit more space. This is the work you can do in a minute. A squared will be equal to 3, negative 1, 2, 7 times 3, negative 1, 2, 7. This is give you a bit of a mind about multiplication, so I'll do it the long way. But 3 times 3 is 9, and then plus negative 1 times 2, and then 3 times negative 1, plus negative 1 times 7, and then 2 times 3, plus 7 times 2, and 2 times negative 1, plus 7 times 7. Remember, we always have to have those brackets. And now we've got 9 minus 2 is 7, negative 3 minus 7 is negative 10, 6 plus 14 is 20, and negative 2 plus 49 is 47. And there's our resultant matrix. That's the value of a squared. Now we can do a squared. This is a very called a one-to-one operation. Squaring a is pretty easy, but taking a square root is quite significantly harder. So you'll never be able to do a square root. Really, you might get a squared as a question as part of a multiplication style thing. There is some context where a squared is a really important value as well. So let's have a look at b squared. Question b is b squared, and b squared is equal to 0, 4, negative 3, that's a 1, 208 times 0, 4, negative 3, 208. And hopefully you can see already that we've got a dimension mismatch, 3 and 2. And we're going to get the same thing with question C, c squared. So what we have now is this last question: what properties make a matrix able to have powers applied? And hopefully you agree that if we've got the same matrix here, we need to have the same number of columns as we have rows in order to allow for that dimension matching, and therefore it must be a square matrix. So for powers to be applied, it must be a square matrix, which was part of our summary at the end of the last video. So let's have a quick look at a your turn, and I'm going to give you a couple minutes to do this now. Okay, well I hope that went well, and let's have a quick look. Hopefully you recognise that y squared is not going to work. X cubed might, so don't fall in the trick of thinking we've got a z there. We could actually do x cubed, and we can do x squared because x is a square matrix. So I'm going to do a first of all. 3, negative 1, 4, 9. There's 4 and 9 in here, it's going to get pretty big. 3, negative 1, 4, 9. This is equal to 3 times 3 minus 1 times 4. Don't need a bucket there. And then 3 times negative 1 and negative 1 times 9. I need a plus here, by the way, and a plus here. 4 times 3, and then 9 times 4 plus, and then 4 times negative 1 plus 9 times 9. Brackets around that, and then evaluate it. 9 minus 4 is 5. Negative 3 minus 9 is negative 12. 12 plus 36 is 48. Negative 4 plus 81 is 77. So there's my solution there. And I suspect I'm going to need a calculator for the next one. So B, question B was our y squared, which was impossible because we have a dimension mismatch. But question C is possible. X cubed is equal to x squared times x. Now if you've got x cubed by itself, you would have to calculate x squared, but we're pretty lucky in this case. We've got x squared, 5, negative 12, 48, 77. We've already done that in part A, and then times by x, which is 3, negative 1, 4, 9. And this is going to be equal to, again, I'm just taking my time to make sure I get this right, 5 times 3 plus negative 2 times 4, 5 times negative 1 plus negative 2 times 9, 48 times 3 plus 77 times 4, and then 48 times negative 1 plus 77 times 9. Okay, and then I need to evaluate that. I'll do the first tuple in my head. So 15 minus 8 is 7. Negative 5 minus 18 is negative 23, so that's okay. And then 48 times 3 plus 77 times 4. You've got to calculate it in your exam, so let's just calculate it. 77 times 4 gives me 452. And then 77 times 9 minus 48, it's the next one, 645. Of course, if we did x to the power 4, this would get even further out of hand. And you can see that this is what we call a diverging multiplication or power here. It's just going to keep on getting larger and larger. Okay, so there's your answers. Hopefully you checked them, you did all right. Obviously, it still holds that you should ask questions as you need to. Exercise 8E is fully open to you now, and you should have a go at it. There aren't a lot of questions there. I've got set 1, set 2, set 3, as we've spoken about. Do set 1 now, do set 2 in 3 days, and do set 3 in 3 weeks. It will really help your knowledge retention. And lastly, remember you can jump on MathSpace for some extra questions. It'll be really handy to be practicing and consolidating this as much as you can. All the best.